Only 4 months ago, this particular comet was entirely absent from our astronomical catalogues. Today it has become one of the most compelling objects in the solar system, and a unique moment of observation is now just 47 hours away. At this very instant, the comet, known as Pan-STARRS, is blazing through its closest approach to the Sun, a point well inside the orbit of Mercury. As it does, its ion tail streams outward, stretching directly across the orbital path of Earth. Our planet is moving toward this invisible ribbon of gas, a quiet and unseen intersection on a schedule no one could have predicted. This alignment coincides with several other cosmic events. A high-speed current of solar wind is already journeying from a coronal hole. A sunspot with a volatile magnetic field is aimed squarely at us, and the Japan Trench continues to settle from the aftershocks of Monday's magnitude 7.4 earthquake. While none of these phenomena are connected, their convergence within the same 4-8-hour window is precisely what makes this story so extraordinary. If this convergence already sparks your curiosity, we invite you to like this video and join us at Calm Space. There are layers to this event we have yet to explore, and you will want to be here as more information becomes available. In less than 2 days, our planet is set to pass through something remarkable. This is not a meteor shower, nor a solar flare, nor anything that can be seen with the naked eye or felt as a physical sensation. So, what is it that awaits us? What Earth is drifting into is an ethereal, magnetically structured filament of ionized gas that extends for hundreds of millions of kilometers across interplanetary space. It is the tail of a comet that few have ever heard of, and the question of whether we can even detect its passage is one of the most fascinating challenges in heliophysics today. The intrigue lies not in any potential danger, as there is none, nor in any visual spectacle, for there will be nothing to see. Instead, the interest is purely scientific, residing at the precise intersection of a rare celestial geometry, profoundly inconvenient timing, and the fundamental limitations of our most sensitive instruments. Let us begin with the comet itself. Officially designated C 2025 R3 Pan-STARRS, it was discovered only a few months ago. Astronomers classify it as a long-period comet, which means its journey originates in the far, frigid reaches of our solar system, a dark territory beyond Neptune, possibly from the Oort cloud itself. From there, it follows a vast orbital arc toward the Sun, a path that requires thousands, or perhaps even tens of thousands, of years to complete. This is very likely its first close passage through the inner solar system, a fact that makes it a pristine and scientifically valuable object. But what makes it so relevant this specific week is its current location and the orientation of its tail. As of now, Pan-STARRS is at perihelion, its closest point to the Sun, a position deep inside Mercury's orbit. The intense heat and radiation at this proximity are causing tremendous outgassing from the comet's nucleus, vaporizing frozen materials and almost instantly ionizing them. This process creates a stream of charged particles that flow away from the Sun, carried by the solar wind, forming the comet's ion tail. And at this moment, that tail is aimed almost perfectly at Earth's orbital track. It is vital to understand exactly what this means, as the language surrounding such events can often be misleading. Earth is not on a collision course with a comet. The comet's solid nucleus is nowhere near our planet. It remains closer to the Sun than any of the terrestrial worlds. What is happening is that Earth is about to cross a line, the geometric projection of where the comet's tail extends through space. You might think of the comet as a distant fire hose pointed in our general direction. The plasma is the water, and it has been spraying toward our orbit for weeks. Earth is simply about to walk through the diffuse spray zone, not the nozzle itself. By the time this plasma reaches us, it will be extraordinarily thin. We are talking about particle densities that are comparable to, and in some areas likely even lower than, the already tenuous solar wind that constantly surrounds our planet. So, if the effect is so subtle, Why does this event matter at all? In science, rare geometric alignments are precious sources of data. This particular configuration, a planet sweeping through the projected ion tail of an active comet, is an event that almost never occurs when we have instruments positioned to measure it. The window for this alignment is incredibly narrow, lasting from April 24 through the 26th, a period of roughly 48 to 60 hours, during which Earth's motion will carry it across the tail's projected path. After this brief period, the geometry will shift, the window will close, and if we fail to capture any useful data, we may not get another opportunity with this specific comet for thousands of years. This fleeting chance raises the stakes for the scientists, hoping to witness a rare cosmic interaction. To be clear about what a detection would entail, we are not anticipating a dramatic event that triggers alerts or appears on public dashboards. Instead, scientists are searching for a subtle but scientifically meaningful signal within the data streams of our spacecraft. This could manifest as a slight rotation of the interplanetary magnetic field, a faint spike in the concentration of heavy ions, or a barely measurable dip in proton density. These are precisely the kinds of faint signatures that the Ulysses spacecraft accidentally recorded when it passed through the tail of Comet Hayakutake in 1996, a landmark discovery that was not even recognized in the data until the year 2000. The story of Hayakutake is a crucial reminder of how elusive these signals can be. The primary complication, and the reason this is happening at the worst possible moment, is that Earth is entering this delicate detection window during one of the most active periods of space weather in recent weeks. The solar wind speed is already elevated, and electron flux has been running high for several days. Furthermore, a magnetically complex sunspot region has emerged on the Sun's Earth-facing disk, and a high-speed stream of solar wind from a coronal hole is forecast to arrive right around April 24th. This means the very 8-hour period when we need the data to be as clean and quiet as possible is shaping up to be the exact opposite. Herein lies the core problem. The challenge is not whether the tail exists or whether Earth will cross it, but whether our instruments can actually distinguish the comet's faint fingerprint from the roaring background noise of an irritable Sunday. In theory, the signal is there, waiting to be found. But whether we can actually hear it above the static is another question entirely. As we consider everything converging on this narrow window, you begin to understand why some scientists will quietly admit that most comet tail crossings are never confirmed. They happen, they pass, and the data sits unexamined in an archive until, perhaps years later, someone notices a strange anomaly and thinks to check the celestial calendar. We are living inside that calendar right now, in a moment that may one day be history. The first thing to understand about a comet's ion tail is that its geometry can be both illuminating and deceptive. We must begin by dispelling a persistent misconception in popular astronomy. The tail does not trail behind the comet like the train of a wedding dress. Instead, the ion tail, also known as the plasma tail, is driven directly away from the Sun by the constant pressure of the solar wind and the interplanetary magnetic field. Its orientation is therefore entirely independent of the comet's direction of travel. In this way, it acts less like a contrail and more like a celestial weather vane, always pointing away from our star. This single fact has profound consequences. For a comet like Pan-STARRS, currently traveling inside Mercury's orbit, this anti-sunward direction means its tail actually points forward relative to its own motion, out toward the more distant solar system. And as orbital mechanics would have it, this orientation happens to align roughly with Earth's current location in space. While these alignments are never exact, models suggest that our planet's path will sweep through the projected region of the tail during the window of April 24th through 26th. But what does it truly mean to cross something so ephemeral? This is where the simple elegance of geometry becomes misleading, and where our understanding of the word crossing must be carefully refined. A comet's tail is not a solid object or even a continuous structure. It is a magnetically sculpted, ever-shifting ribbon of ionized molecules, fragments like water and carbon monoxide ions, which are torn from the comet's nucleus by solar radiation. Near the comet's head at its closest approach to the Sun, this material is dense enough to be spectacular. But as it extends outward across millions of kilometers, its density drops dramatically. The tail becomes a gossamer, nearly transparent feature, existing more as a pattern within the magnetic field than as a tangible concentration of matter. The solar wind further complicates this delicate structure. As the solar wind pushes and twists the interplanetary magnetic field, it distorts the tail's shape in real time. The tail writhes, it kinks, and it can even experience disconnection events where large sections physically break off and drift away, triggered by sudden shifts in solar conditions. It is a dynamic, flickering stream, with new material constantly flowing from the nucleus as older material gets diluted into the background plasma flow. This dynamic reality is the crux of what scientists call the gap between probability and detectability. The orbital mathematics indicates a relatively high probability that Earth will geometrically pass through the region once occupied by Pan-STARRS' tail. The calculations put us in the right zone at the right time. However, the probability that the tail will still possess a coherent, detectable structure at Earth's position is an entirely different and far more uncertain question. It is one thing to know you are in the path of a storm. It is another to know if the storm will still be there when you arrive. An earthly analogy may help to clarify this deep uncertainty. Imagine a long road that was briefly covered in snow a week ago. In the time since, the snow has been partially melted by the sun, blown into patchy drifts by the wind, and refrozen into strange patterns. You can still find traces of where the snow once lay if you know precisely where to look, but you could not honestly describe the road as snowy in the present moment. At Earth's vast distance, the comet's tail is much like that weathered patch of snow. The material is there, or at least it was there, somewhere in that broad spatial zone. Whether Earth will happen to sweep through a patch coherent enough to leave a measurable imprint on our instruments is, for now, genuinely unknown. A significant part of this uncertainty stems from our inability to map the tail's density in real time. We cannot view it on a screen the way a meteorologist tracks a weather system with radar, nor can we dispatch a probe to check the conditions ahead of Earth's arrival. The only way to know for certain what lies at our specific position in space is to be at that position and to measure it directly. This is precisely the task of the spacecraft positioned at the Lagrange 1 point and elsewhere during the encounter window. These observational limits are compounded by the fundamental limitations of our predictive models. The simulations that forecast the tail's location and density are built upon a foundation of assumptions about solar wind conditions, the comet's outgassing rate, magnetic field geometry, and dozens of other variables, each carrying its own degree of uncertainty. A small error in any one of these inputs can translate into a large discrepancy in the predicted location and density of the tail. Scientists can say the tail should be in a general region, but they cannot state with certainty that it will be dense enough to detect at a specific time. This leads to perhaps the most counterintuitive point of all. A perfect geometric crossing does not guarantee a measurable event. The outcome depends entirely on whether the signal can rise above the background noise floor, and at this moment, that noise floor is not cooperating. To understand the potential for discovery, we can look to a remarkable precedent that was almost missed entirely. In May of 1996, the Ulysses spacecraft was on its unique mission, charting the solar system from a high-latitude trajectory, when its instruments recorded something strange. The data showed a sharp rotation in the interplanetary magnetic field, accompanied by a sudden drop in proton density by roughly half. At the same time, sensors designed to measure ion composition, registered the presence of heavy ions, such as oxygen and carbon, at concentrations that did not match the typical solar wind background. At the time, no one on the mission team noticed. The data was simply recorded, archived, and filed away with countless other readings as Ulysses continued its journey. It was not until the year 2000, 4 years later, that a team of researchers re-examined the 1,996 data. By comparing those unusual readings to the orbital trajectory of Comet Hayakutake, they finally realized what had happened. Unbeknownst to anyone, Ulysses had crossed Hayakutake's ion tail. This encounter did not happen near the comet, nor anywhere close to it, providing the first concrete evidence that a comet's influence could be detected at such an immense distance. The crossing itself took place at an immense distance of 3.8 astronomical units from the comet's core, a journey of roughly 360 million miles. It was a staggering revelation that the ion tail could stretch that far and remain intact. Once researchers understood what to search for, the signature, hidden in the data, became undeniable in retrospect. This event provides the crucial historical precedent that makes the window for observing Pan-STARRS so compelling for science. It serves as definitive proof that a comet's ion tail can preserve a detectable structure across extraordinary distances. It confirms that our spacecraft are capable of recording real, measurable effects when they pass through these tenuous structures. And perhaps most importantly for this story, it demonstrates that such groundbreaking signatures can lie dormant in our archives for years, waiting for a curious mind to uncover them. To appreciate the challenge Earth faces, we must first understand what made the detection of Hayakutake's tail so scientifically clean. The Ulysses spacecraft was a solitary observer, navigating a quiet and relatively empty region of interplanetary space. At its location, the background conditions of the solar wind were remarkably stable. There were no complicating factors, such as a high-speed stream from a coronal hole that could warp the magnetic field's geometry. The data was not clouded by an elevated flux of electrons that would otherwise interfere with ion composition readings. Crucially, the spacecraft was not enveloped within a planet's magnetosphere, which introduces its own complex layers of interference. Ulysses was simply performing its mission in the pure solar wind when the comet's tail silently drifted past. The signal itself was composed of 3 distinct and corroborating components. First, there was a rotation in the magnetic field. The interplanetary magnetic field lines abruptly changed their orientation at the boundary of the tail. This was the classic signature of magnetic draping, a process where the sun's magnetic field wraps around the material, gassing out from the comet's nucleus, and is stretched far back into space. Second, instruments registered a noticeable drop in density. Inside the tail, the density of protons fell, which is consistent with a region where the comet's own plasma has partially pushed aside the normal solar wind. Finally, there was the detection of heavy ions, specifically oxygen and carbon ions appearing at concentrations well above the background level. These were the direct chemical fingerprints of the cometary material itself. Taken individually, none of these 3 signals would have been conclusive. The magnetic rotation could have been dismissed as a standard discontinuity in the solar wind. The drop in density might have been interpreted as the passage through a quiet sector. Even the presence of heavy ions could have been attributed to trace contamination from other sources. But the combination of all 3, perfectly aligned in time along a trajectory that could be traced directly back to Comet Hayakutake, made the case irrefutable. Even 4 years after the event, this convergence of evidence is what transforms a possibility into a scientific certainty. Now, we must consider the critical difference. Earth's encounter this week is nothing like Ulysses' journey through a quiet patch of space. Our planet is enveloped by a powerful magnetosphere. While we have a whole fleet of spacecraft monitoring this region, they are all operating within an environment that is already magnetically complex. This environment is already experiencing elevated fluxes of energetic particles and is, at this very moment, about to be impacted by a high-speed stream from a coronal hole. The very signatures that so clearly identified Hayakutake's tail, the magnetic rotation, the density drop, and the heavy ions are precisely the kinds of phenomena that these solar wind disturbances can create on their own, with no comet required. This presents the detection challenge in its starkest form. The question is not whether a signal exists, but whether we can distinguish that specific signal from all the other cosmic noise that mimics it. This leads to a deeper, more unsettling implication. Even if we cannot definitively answer that question right now, and even if the data from April 24th through the 26th returns ambiguous or seems completely overwhelmed by solar activity, it does not mean that nothing happened. It may simply mean we are living through the beginning of another Hayakutake story. The data will be archived, and in 2, 3, or perhaps 5 years, another researcher may look at it with fresh eyes. They may find exactly the signature we are hoping for, or they may find nothing. Both outcomes are scientifically informative and require that the data be meticulously preserved. But with only 47 hours remaining on the clock, the immediate question is whether anyone will notice anything at all. And to understand that, we must first confront the noise. The initial complication in this search is not a dramatic, isolated event. Before we even consider the approaching sunspot and coronal hole, it is essential to establish the baseline space weather environment. Even the ordinary background conditions at this moment are not what scientists would consider favorable for such sensitive detection work. The stage is already set for a difficult observation. For the past several days, the solar wind speed has been consistently running above 500 kilometers per second. To place that figure in context, the average speed of the solar wind is typically between 400 and 450 kilometers per second. A reading of 500 plus is elevated, though not yet dramatic. It is akin to the difference between a steady breeze and a persistent, stiff wind. In practical terms, this means the magnetic field environment around Earth is more dynamic, more variable, and more susceptible to short-term fluctuations. These fluctuations can easily appear as anomalies if they are not carefully accounted for, creating potential false positives. Meanwhile, the flux of electrons has been sustained at high levels for multiple consecutive days. This elevated electron flux is partly a result of heightened solar activity and partly a function of geomagnetic conditions. This charge tends to build up during active periods and can linger for days before returning to baseline levels, even after the initial driving conditions have subsided. For instrument operators, a sustained high electron flux is a significant concern for data quality. It acts like background static in certain measurements and can interact with the spacecraft themselves, introducing systematic errors into the data if not meticulously corrected. Adding to this complex picture are the current geomagnetic conditions. Activity measured by the KP index, which ranges from 0 for complete quiet to 9 for the most extreme storms, has been hovering in the quiet to unsettled range, with brief spikes toward active. While this is fairly typical for the current phase of the solar cycle, it is a crucial detail. It tells us that Earth's magnetosphere is not in a pristine, dormant state. It is already mildly agitated, jostled by the ongoing elevated solar wind. A mildly excited magnetosphere inherently means more baseline variability in the measurements taken by spacecraft operating in the near-Earth environment. This combination of factors creates the fundamental problem for the detection we are hoping for. Our instruments do not simply detect events, they detect changes. More specifically, they detect changes that are significant enough relative to the ambient variability to be statistically distinguished from the background noise. If that background is stable and quiet, even a very small signal can stand out with perfect clarity. But when the background itself is an unpredictable and fluctuating tapestry, a faint, subtle signal risks being lost entirely. When the background itself is already in flux, flickering with the telltale signs of elevated solar wind, fluctuating electron activity, and mild geomagnetic unrest, any small signal becomes buried. This is a critical distinction. The signal does not vanish from the data. Mathematically, it remains present, but it is now concealed beneath the noise floor. Extracting it demands statistical methods that, in turn, introduce their own layers of uncertainty. A helpful way to visualize this is to imagine hearing someone whisper your name from across a large, crowded room. In complete silence, you might discern it from 10 meters away. But if that same room is filled with dozens of conversations, ambient music, and the occasional crash of a dropped object, you could miss the whisper entirely, even from just 3 meters. The sound of your name is still there. The sound waves are still reaching your ears. The problem is that the signal-to-noise ratio has dropped below the threshold where your brain can reliably isolate it. This is almost precisely the environment our spacecraft are now navigating. The faint signature of the comet's tail, if it is detectable at all, is the whisper. The current space weather is the noise in the room, and even before the anticipated coronal hole arrives, that room is already far from quiet. One of the most challenging aspects of this work is what scientists refer to as false positives. The fluctuations within the solar wind are not chaotic in the same way that electronic background noise is. Instead, they possess structure. They arrive with their own magnetic field rotations, shifts in density, and variations in composition that trace back to different source regions on the Sunday. The danger is that any of these structured fluctuations could, by sheer coincidence, mimic the signature of a comet tail crossing. An abrupt rotation in the interplanetary magnetic field might have nothing to do with a comet. A sudden drop in density could be caused by a transient, quiet sector of the solar wind. Trace heavy ions might be the lingering remnants of a solar energetic particle event. Any of these phenomena, alone or in combination, could easily be misinterpreted as a tail signature by an observer eager to find one. But the reverse is also true, and this is the part of the puzzle that keeps the scientific process honest. A genuine signal from the comet could be dismissed as just another solar wind fluctuation by someone who wasn't expecting it. This is exactly what occurred with the data from Comet Hayakutake, which went unrecognized for 4 years. To find a definitive answer, the data will require a painstaking forensic analysis. It must be filtered, corrected for instrument behavior, and compared against sophisticated models of the background solar wind. Furthermore, it needs to be cross-checked against measurements from multiple instruments and even multiple spacecraft. This rigorous process takes months, not hours. This means the answer to the question of whether we detected the tail of Comet Pan-STARRS will not arrive in a press release on April 26th. It will emerge, if it emerges at all, from a carefully prepared scientific paper, likely published a year or more from now by a team that has spent countless hours debating how to separate the whisper from the noise. And all of this assumes that the sun cooperates. As it happens, our star is about to do precisely the opposite. Something new has been growing on the face of the Sunday. It began as a modest cluster of magnetic disturbance just a few days ago, but it has been developing with remarkable speed. As of this recording, it has earned a classification that makes space weather forecasters pay very close attention. Active region 4420, catalogued with a beta-gamma magnetic configuration. That technical label is profoundly important. Sunspot regions are categorized based on the complexity of their magnetic topology, the way their north and south polarity fields are arranged. A simple alpha or beta configuration implies that the opposing polarities are well separated and relatively stable, making them unlikely to suddenly reconnect and release vast amounts of energy. A beta-gamma configuration, however, means the polarities are tangled and interwoven at their boundaries. This creates the kind of topological stress that makes magnetic reconnection and the explosive solar flares it powers far more probable. Active region 4420 has now expanded to cover roughly 180 millionths of a solar hemisphere. While substantial, this is not a record-breaking size. It contains approximately 15 individual sunspot umbrae, all arranged in a layout that forecasters have described as magnetically complex and continuing to evolve. In terms of immediate risk, flare probabilities over any given 2-4 hour period have been running at around 75% for class events, which are considered moderate flares. More significantly, the probability for M-class events which are larger and more energetic has been holding at around 10%. An M-class flare erupting from a well-positioned active region is precisely the kind of event that can produce measurable effects here at Earth. These can include elevated proton fluxes, increased absorption in the ionosphere, and potential geomagnetic activity if the flare is accompanied by a coronal mass ejection. To be perfectly clear about the current threat assessment, as of this recording, no major Earth-directed coronal mass ejections have been observed originating from AR 4420. The region has certainly been active, but it has not yet produced the kind of eruption that would hurl a significant cloud of plasma directly toward our planet. The flares it is generating are producing X-ray bursts that are already affecting high-frequency radio propagation on Earth. But this is a routine consequence of moderate solar flaring. The more dramatic scenarios, the ones that would fundamentally alter the space weather environment for the next several days, have not yet come to pass. But the operative word in that sentence is times yet. And this is where active region 4420 connects directly back to the search for Pan-STARRS' tail. Even without a major coronal mass ejection, an active sunspot region constantly perturbs the sun's magnetic topology. It generates outflows of energetic particles and creates subtle variations in the solar wind that emanates from the areas surrounding it. In doing so, it introduces a new layer of complexity into the interplanetary magnetic field. This is the very same magnetic field that the comet's tail is threaded through, and the very same field whose rotational signatures would serve as a primary indicator of a detection. The presence of this active region fundamentally changes the nature of the search. Think of the interplanetary magnetic field as the vast, invisible fabric of our solar system. The comet's tail, as it passes through, should leave faint patterns in that fabric, subtle wrinkles, distortions, and magnetic draping structures that our spacecraft are designed to measure. But an active sunspot region like AR 4420 is constantly sending out its own ripples across that very same fabric. These solar ripples do not cancel out the comet's patterns. They overlap them. They mix with them. From an instrument's perspective, an overlapping ripple from the active region looks almost identical in kind, if not in magnitude, to the patterns a comet tail would leave behind. This is the detection problem viewed from the other side, not from the faintness of the signal, but from the loudness of the solar noise. The sun is not deliberately trying to hide the comet's tail from us. It is simply being the Sunday. The consequence, however, is the same. A higher noise floor, a more complex magnetic environment, and a much harder job for the scientists, who will eventually try to find something extraordinary hidden within the data. The situation was already challenging enough, even before this new variable came into play. As if the complexities of tracking active region 4420 were not enough, another celestial event is approaching, and its timing presents a truly remarkable inconvenience. This new factor is a coronal hole, a feature on the sun poised to alter the entire environment of our search. In the sun's upper atmosphere, the corona, there are vast areas where the magnetic field behaves differently. Instead of looping back to the solar surface, these magnetic field lines extend far out into space, creating open channels. Along these pathways, solar material escapes as a continuous stream into the heliosphere. Because these regions are cooler and less dense, they appear as dark patches in extreme ultraviolet and X-ray light, earning them the name coronal holes. The solar wind that flows from these openings is distinct from the sun's typical outflow. It is significantly faster, less dense, and carries its own unique magnetic orientation. This is not just a minor variation, but a fundamentally different type of solar weather. A high-speed stream from a coronal hole does not travel through the solar system in isolation. As it rushes outward, it inevitably overtakes the slower solar wind that departed from the sun earlier. This interaction creates a fascinating and disruptive phenomenon. At the boundary where the fast wind collides with the slow wind, plasma piles up, forming a compressed and turbulent structure known as a co-rotating interaction region, or CIR. This region is a swirling zone of intensified magnetic fields and higher particle densities. Because it is tied to a feature on the rotating sun, a CIR sweeps past Earth like a lighthouse beam, reappearing roughly every 27 days. While not as explosive as a direct hit from a coronal mass ejection, these recurring interaction regions are potent drivers of geomagnetic activity, capable of creating sustained disturbances that are magnetically complex and challenging to predict in detail. The specific coronal hole causing this event has been monitored for days, and its associated high-speed stream is forecast to reach Earth on or around April 24th. In a stroke of cosmic misfortune, this is the very same day that the window opens for a potential crossing of Comet Pan-STARRS' tail. Forecasters anticipate the solar wind speed will surge to between 600 and 700 kilometers per second, a dramatic increase from the already brisk background of 500 kilometers per second. The expected geomagnetic response is a KP index of 4 to 5, which translates to active or minor storm conditions. This is enough to generate auroras at higher latitudes and increase atmospheric drag on satellites in low Earth orbit. More critically for our search, it is certain to fundamentally reconfigure the magnetic environment around our planet, creating a powerful signature in all spacecraft data. The challenge this high-speed stream poses to detecting the comet's tail is multifaceted. On one level, it creates a problem of mistaken identity. The arrival of the stream's leading edge will cause rapid and dramatic shifts in the interplanetary magnetic field at Earth's location. This is precisely the kind of anomalous signal a scientist would look for as a potential indicator of a comet tail crossing. An observer who sees a sharp rotation in the magnetic field data on April 24th might initially suspect they have found the comet's signature. However, the far more likely cause will be the boundary of the incoming coronal hole stream, creating a powerful false positive. On a deeper level, the turbulence stirred up by the stream's passage physically compromises the comet's tail itself. The delicate structure of an ion tail is sculpted and maintained by the steady pressure of the solar wind, which drapes the sun's magnetic field around the cometary material. A sudden blast of faster, magnetically different wind will disrupt this fragile form. The fast wind from the coronal hole could accelerate parts of the tail, stretch other regions, and compress still others, smearing out its structure. The clear, coherent magnetic signature that the Ulysses spacecraft detected at Comet Hayakutake was only possible because a relatively stable solar wind carried that structure intact across space. A coronal hole stream is the very opposite of stable conditions. Buried within this challenge is a paradox that makes space weather science so compelling. In theory, more solar activity means more energy, more particles, and a richer, more complex data environment. This heightened activity could potentially create new, secondary effects as the solar wind interacts with the comet's ions, perhaps producing a unique particle signature that wouldn't exist in a quiet solar wind. But this same enhancement of activity introduces an overwhelming amount of background noise. It is a classic observational dilemma. The very events that make the space environment most interesting are also the ones that make subtle signals the most difficult to isolate. In this case, the coronal hole stream is not merely adding noise. It has become the dominant signal, arriving just when the highest possible signal-to-noise ratio is needed. For those of us on Earth's surface, the geomagnetic effects of a KP4 or 5 event are generally minor. Some disruptions to radio communications, operational adjustments for satellites, and perhaps a faint aurora for observers above 50 degrees latitude. But for the scientists and the spacecraft collecting the data, these conditions represent a monumental analytical challenge. Every single measurement will have to be painstakingly corrected for the background signature of the coronal hole stream before the team can even begin to search for the much fainter trace of the comet's tail beneath it. The window of opportunity is closing, the floor of background noise is rising, and the faint signal we are searching for grows no stronger. There is another fundamental aspect of this search that is easy to miss. The material within the comet's tail is not some exotic, alien substance that would immediately stand out in any dataset. It is composed of ordinary gas molecules, water, carbon monoxide, carbon dioxide, that have been ionized by solar radiation. Once stripped of electrons, they become charged particles that interact with magnetic fields, forming a plasma. This composition is not dramatically different from the solar wind itself, which is also a plasma made mostly of protons and electrons, with traces of helium and other heavier ions. The boundary between the comet's plasma and the solar wind is not a sharp, clear line. Instead, it is a gentle gradient, a region where the ratio of cometary ions to solar wind ions gradually shifts. Detecting this faint gradient requires instruments with the precision and stability to notice an incredibly subtle change in the plasma's chemical recipe. The search is not for something different, but for a slight change in the balance of something that is already there. The search for a comet's tail hinges on detecting a subtle anomaly, perhaps a slight excess of oxygen ions, or an elevated concentration of carbon-bearing molecules beyond what the pure solar wind should contain. Yet, this immediately presents a fundamental challenge. The solar wind is not a clean background. It already carries trace amounts of these heavier ions. Oxygen, carbon, silicon, and iron are all present in small quantities, material carried away from the sun's own corona, which is not made of pure hydrogen. The elemental ratios within this wind are constantly shifting, dependent on the solar source region, the local coronal temperature, recent flare activity, and a host of other variables. These fluctuations occur over timescales as short as a few hours, meaning that to identify a faint cometary signal, scientists must first know with great precision what the normal background was for that exact parcel of wind at that exact moment, a task of immense difficulty. This complex puzzle becomes even more intricate with the arrival of a coronal hole high-speed stream. The fast wind originating from these coronal holes possesses a distinctly different elemental signature than the slow wind. It exhibits different oxygen charge state ratios and unique iron-to-oxygen abundance patterns. While these changes are well documented and can, in principle, be modeled and removed from the data, they add a formidable layer of complexity to the analysis. Trying to detect a comet tail signal on top of the compositional shift from a high-speed stream is like trying to hear a single, faint violin note while an entirely new, louder section of the orchestra begins to play. The original note, if it's there at all, becomes overlaid, mixed, and partially masked. A trained ear with the right analytical tools might still isolate it, but the uncertainty in doing so grows substantially. Here, the concern about the signal being absorbed is very real. This is not a physical absorption, where the comet's plasma is destroyed by the encounter. Rather, It is an absorption into the data itself, where the signature of the tail's presence may become indistinguishable from the natural variations of the background. This can happen not necessarily because the signal is too small in absolute terms, but because the background variability during the event is so large that it can easily encompass the signal's magnitude. In essence, the sought-after signal falls entirely within the error bars of the surrounding noise, rendering it statistically invisible. There is also a specific concern regarding discontinuities in the interplanetary magnetic field, or IMF. The solar wind is not a smooth, uniform outflow like water from a tap. It is a turbulent medium, filled with current sheets and thin boundaries that separate regions of different magnetic polarity. At these discontinuities, the field direction, speed, or density can change abruptly. Such events are a normal feature of the solar wind, occurring regularly every few hours at Earth's location, caused by everything from stream interactions to instabilities developing within the wind itself. The uncomfortable truth is that some of these routine discontinuities produce magnetic signatures that look remarkably similar to what one would expect from a comet tail boundary. A sharp rotation of the magnetic field vector, a change in plasma density, and perhaps even a compositional hint. The famous Hayakutake crossing, for instance, featured a clear IMF rotation as one of its key identifying signatures. But so does an ordinary solar wind sector boundary crossing. The two phenomena are not identical, of course. There are subtle differences in the specific shape of the magnetic rotation, the accompanying density behavior, and the ion composition. However, these are not the kind of differences that are immediately obvious. They are the kind that require painstaking, multivariable analysis to establish. They will not simply jump out from a first pass of the data, which makes distinguishing a genuine cometary encounter from a coincidental solar wind event a profound challenge. Scientists studying this problem are acutely aware that they may be left with a dataset that is genuinely ambiguous. Not incomplete or wrong, but ambiguous in the sense that two equally valid interpretations could explain the same observations. A comet tail crossing on one hand, or a solar wind fluctuation coinciding with the arrival of a high-speed stream on the other, might both fit the data. Without additional constraints that the current configuration of instruments may not be able to provide, cleanly separating these two possibilities could be impossible. This ambiguity is not a failure of the scientific method. It is an honest reflection of its rigor. But it is also why the answer to the central question, did we detect the tail of Pan-STARRS, may remain genuinely uncertain for a very long time. To understand the stakes, it is worth mapping out the possible outcomes. In the absolute best-case scenario, the data from April 24th through the 26th would reveal a clean, unmistakable sequence of events. First, an IMF rotation of the right kind at the right time, followed by a telltale density change, and finally, a compositional anomaly bearing the clear fingerprint of cometary heavy ions. Ideally, multiple spacecraft at different locations would register consistent signals, and the coronal whole high-speed stream would arrive either just before or just after the crossing window, leaving a brief, clean interval in the data. With a cooperative solar wind, the background could be modeled and subtracted with confidence, allowing a team to publish a paper within a year declaring, "We detected it." Such a result would be nothing short of extraordinary. It would represent only the second well-documented instance in history of Earth's environment registering the passage of a comet's ion tail. The first case, involving comet Hayakutake, was not even detected in real time. It was discovered years later by scientists combing through old data. A real-time or near real-time confirmation of such an event would therefore be a genuine breakthrough for heliophysics. In the worst-case scenario, the high-speed stream arrives precisely on schedule, pushing the KP index to 5 or higher and plunging Earth into a geomagnetic storm during the crossing window. The solar wind would become turbulent and compositionally variable, and every dataset from that 4-8-hour period would be completely dominated by the storm's signatures. The comet tail's signal, if it was ever there, would be entirely buried beneath the noise. Later analysis would find it impossible to separate any potential cometary trace from the overwhelming background, resulting in a null detection, not a confirmed absence, but an inability to confirm a presence. The crossing likely happened, but the data would simply be too messy to prove it. Between these two extremes lies the vast and more probable middle ground. In this outcome, the data would contain some anomalies around the expected time period. These anomalies would be consistent with a tail crossing, but they would not be definitively attributable to it. The evidence would be tantalizing, suggestive, but ultimately inconclusive. It is in this gray area of ambiguity that scientists often find themselves, grappling with data that whispers possibilities rather than shouting certainties. Anomalies in astronomical data can sometimes spark a brief, intense scientific debate that may or may not lead to a settled consensus. Here, we encounter an observational paradox at the very heart of our story. The viewing window is a real period of time. The geometry of the encounter is genuine, and the comet itself is undeniably present. The challenge, however, is that the very act of observation is being compromised by factors far beyond anyone's control. There is a profound philosophical question embedded in this, suggesting a universe that can present these remarkable, fleeting chances for discovery, only to have other physical processes obscure our view. It is a reminder that science has navigated such challenges before, not with comet tails specifically, but with the universal problem of isolating a clear signal from a complex and noisy background. The detection of gravitational waves, for instance, demanded instruments of unimaginable precision, capable of measuring a distortion smaller than a proton while filtering out the constant vibrations from earthquakes, traffic, and even thermal changes. Similarly, discovering exoplanets requires spotting stellar brightness dips of less than 1% and distinguishing them from a star's own natural fluctuations. The field of heliophysics is not alone in this struggle. It is simply facing a particularly acute version of it this week. The Sun is complicating the data, and Earth's own dynamic environment is adding to the noise. And now, something entirely different is poised to introduce yet another layer of confusion. An event with no connection to comets or solar wind, but one that will collide with this story in the public mind in ways that demand careful examination. The Japan Trench is still moving. This brings us to Part 9, the Japan Trench timing problem. On April 20th, a powerful megathrust earthquake, registering between magnitude 7.4 and 7.5, occurred off the coast of Japan. It originated along the Japan Trench, one of the most seismically volatile subduction zones on our planet. What makes this earthquake so significant to our narrative is its timing relative to the other events we have been discussing. It is not that the earthquake is physically related to the comet or the sun's activity, it is not. The crucial detail is that it happened first. It struck before the coronal hole became a factor, before the peak viewing window for Pan-STARRS' tail crossing, and before all the other cosmic events began to converge. This temporal sequence is fundamentally important for understanding how and why these separate occurrences will inevitably become intertwined in the popular narrative. Following a major megathrust earthquake, the resulting sequence of aftershocks adheres to a well-documented statistical model known as the Omori-Utsu law. This law describes how the frequency of aftershocks predictably decreases over time. A large number of aftershocks occur immediately after the main event, with their rate diminishing as time passes, though never reaching zero for a considerable period. An earthquake of magnitude 7.4 along the Japan Trench is expected to produce aftershocks for weeks, perhaps even months, with larger tremors of magnitude 4.5 to 5 scattered throughout the sequence. These aftershocks tend to be concentrated spatially along the fault segment that initially ruptured. The ongoing aftershock activity, as Earth moves into the April 24th to 26th window, aligns perfectly with this established pattern. Multiple events of magnitude 4.5 and higher have been recorded since the main shock, all occurring where the models predict and at the frequency forecasted by the Omori-Utsu law. From a seismological standpoint, there is nothing unusual about them. The probability of a significant aftershock, technically, one in the magnitude 5.5 to 6 range or larger, is approximately 5 to 6% in any given week for a sequence of this scale. This risk is not negligible, but it is also not heightened by any of the concurrent events happening in space. The seismic hazard in this region is what it has always been, governed by the immense mechanical stress within the subducting Pacific plate. That geological stress state remains entirely uninfluenced by the geometry of a comet's plasma tail or the speed of the solar wind. The forces at play are terrestrial, deep within our planet, and indifferent to the happenings of the solar system. Here, the detection problem we have been tracing finds an unexpected mirror in a different domain. Just as interpreting spacecraft data during the April 24th window is complicated by multiple physical processes creating similar signals, the public narrative surrounding these events faces a parallel challenge. A series of distinct, real events, an earthquake sequence, heightened solar activity, and a comet tail crossing are all converging within the same narrow time frame. The human mind, however, is notoriously, almost pathologically, ill-equipped to accept such simultaneous events as mere coincidence. This is the essence of the timing problem. The timeline itself is the key to maintaining clarity. The earthquake struck on April 20th, and the comet tail crossing window opens on April 24th. This 4-day gap is significant, as it clearly separates the two events in time, and causality does not operate in reverse. The complication is that the aftershocks are still ongoing, creating a continuous seismic sequence that blurs the timeline for a casual observer. From the outside, seeing headlines about an earthquake sequence, a comet, and a solar storm all in the same week can make the order of events seem indistinct. It is in this blurring of the timeline that false narratives are born. The earthquake preceded every other event in this story. It did not cause them, nor was it caused by them. Understanding this is not merely an academic exercise. It is the crucial distinction between seeing this week's events as a series of independent coincidences or as an interconnected phenomenon. The data is clear that they are the former, but clear data and a compelling story have never been the same thing. This leads us to part 10. The narrative collision. At this stage in the story, the internet is already a hive of activity. Anyone searching for terms like Pan-STARRS, plasma tail, or comet Earth in the last 48 hours has likely encountered claims ranging from the speculative to the entirely baseless. The most prevalent of these, and the one that warrants direct attention because it appears the most scientific, follows a particular line of reasoning. It suggests that incoming plasma from the comet's tail is electromagnetic, that such influences from space can affect Earth's geomagnetic field, and that geomagnetic disturbances have been statistically linked to increased seismic activity. Therefore, the argument concludes, the comet is either contributing to or directly triggering the aftershocks in the Japan Trench. Each individual step in that logical chain contains a mixture of truth and fiction, woven together in a way that makes the proposition seem plausible. The overall conclusion, however, is not supported by the evidence. To understand why, we must carefully walk through each part of the claim. It is true that the material flowing in a comet's plasma tail is electromagnetic. It is composed of charged particles and carries magnetic fields, and any interaction with our planet would, in principle, influence Earth's own geomagnetic field. However, the scale of such an effect is the crucial detail. This interaction is technically accurate, in the same way that a single feather landing on the roof of a building measurably alters its downward momentum. True, in theory, but entirely irrelevant in any practical sense. For decades, researchers have explored potential links between geomagnetic disturbances and seismic events, creating a body of literature that is vast, contentious, and ultimately inconclusive. While a few statistical studies have claimed to find weak correlations under very specific circumstances, a far larger number of papers have found no significant relationship at all. Even more telling, none of the studies suggesting a link have proposed a physical cause that is remotely plausible given the immense energies required. But for this particular claim, the physics is almost secondary to a much simpler, more fundamental problem: the timeline. The earthquake struck on April 20th. The window for Earth's interaction with the comet's plasma tail did not even begin until April 24th. In our universe, causes must precede their effects. The comet's plasma could not have traveled backward through time to fracture a tectonic plate 4 days before its arrival. This simple fact alone is enough to dismiss the hypothesis entirely. And yet, the persistence of such ideas raises a deeper question about why these narratives feel so compelling to us in the first place. The human brain is a magnificent pattern recognition engine, an instrument perfected by evolution to find connections within noisy and complex environments. It is a survival trait to observe seemingly random occurrences and ask, are these related? While this ability has served our species incredibly well, it also has a predictable flaw. It systematically generates false positives. This happens whenever multiple dramatic or unusual events unfold in close succession. We are instinctively wired to notice the alignment, to feel the weight of the convergence, and to resist the simple, often correct, explanation of mere coincidence. The convergence of events during that week was statistically real. 5 separate and unusual phenomena occurred within a 4-8-hour period. But rarity does not imply connection, and the powerful feeling that something is significant is not, by itself, evidence that it is. This may be the most vital lesson of all. We must learn to separate a compelling story from the signal it purports to explain, a discipline that applies just as much to analyzing comet data as it does to evaluating world events. The most direct way to assess any claim that space weather can cause earthquakes is to ask a single, dispassionate question: do the numbers add up? This isn't a philosophical query or a search for statistical correlation, but a raw comparison of energy. Does the energy delivered by the space weather event even approach the energy needed to trigger a seismic rupture? A magnitude 7.4 megathrust earthquake, like the one in question, unleashes approximately 10 to the 15th joules of energy. This is a staggering figure, roughly equivalent to the simultaneous detonation of tens of thousands of nuclear weapons. This power originates from the slow, relentless buildup of elastic stress between tectonic plates over hundreds or even thousands of years. A vast mechanical spring compressed over geological time, then released in a matter of seconds. By contrast, the electromagnetic energy delivered to our planet's environment during its passage through a comet's ion tail is orders of magnitude smaller. Even using the most generous estimates for the tail's density at Earth's orbit, the energy involved is perhaps 12 to 15 orders of magnitude less than that of the earthquake. This means we are comparing the energy of the quake to something that is a trillion or even a quadrillion times weaker. The comet's electromagnetic footprint, while potentially detectable by highly sensitive spacecraft, would be utterly imperceptible as a mechanical force acting upon the solid crust of the Earth. Even the most powerful space weather phenomena we know of, such as major geomagnetic storms driven by large coronal mass ejections, fall dramatically short. These are events capable of causing widespread power grid failures and damaging satellites, yet they still do not deliver sufficient energy to the solid Earth to meaningfully alter the stress on a locked fault line. The simple reason is that the coupling between electromagnetic effects in the upper atmosphere and the mechanical behavior of the lithosphere below is extraordinarily weak. The planet's crust does not respond to magnetic field fluctuations like a compass needle. It responds to immense physical stress and strain, measured in megapascals and built up over centuries. When we look closely at the scientific literature on solar seismic correlations, any proposed relationships involve effects so minuscule they are barely distinguishable from statistical noise. The mechanisms suggested, from subtle changes in atmospheric pressure to the modulation of ionospheric currents, all operate at energy scales far, far below what is needed to initiate a major earthquake. At the absolute most, a few researchers have speculated that a space weather event might act like a single, final grain of sand on an already unstable pile, slightly altering the timing of a rupture that was already critically stressed and about to happen anyway. But even this is highly speculative, and many claimed correlations have been shown to be mere artifacts of statistical analysis. Ultimately, the theory connecting the Pan-STARRS comet to the Japan Trench earthquake fails on every conceivable level. The energy budget is wrong by more than 10 orders of magnitude. The timeline is impossible, with the effect preceding the cause by 4 days. There is no plausible physical mechanism to connect the two. The claim simply does not survive its first contact with physics. The fact that we must even articulate this argument, however, is itself a signal worth detecting. It tells us that distinguishing a real signal from ambient noise is a profound challenge, not only for scientists analyzing spacecraft data, but for all of us navigating public discourse in the modern world. So, if you wish to identify the actual, documented, and operationally significant risk associated with the space weather conditions of that late April window, you must stop looking down at the ground. Instead, you need to start looking up into orbit. A persistent, multi-day surge in electron flux poses a quiet but genuine danger to orbiting spacecraft. This isn't the type of threat that generates dramatic headlines, but it is a constant concern for operations teams, as it contributes to the slow degradation and eventual failure of satellite components over time. The process responsible is known as deep dielectric charging. It begins when high-energy electrons bypass a satellite's outer shielding, embedding themselves within the non-conductive or dielectric materials of its electronics. This accumulation of charge can reach a tipping point, leading to a sudden internal discharge. The resulting current pulse acts like a tiny bolt of lightning deep within a circuit board, capable of damaging sensitive components without warning. Not all satellites face the same level of risk. Those in low Earth orbit benefit from the protection of our planet's magnetic field. However, spacecraft in medium Earth or geosynchronous orbits, including vital GPS, communication, and weather satellites, are far more exposed. In response, ground teams implement careful precautions, pausing radiation-sensitive operations, watching charge indicators, and preparing contingency plans. Beyond internal charging, heightened geomagnetic activity brings other familiar challenges. For low-orbit satellites, the upper atmosphere expands, increasing drag that necessitates corrective engine burns to maintain altitude. Simultaneously, ionospheric fluctuations can degrade GPS precision and disrupt high-frequency radio communications vital to aviation and shipping. These are not sensational scenarios, but well-documented and economically significant consequences of space weather's interaction with our technology. This complex environment leads directly to what is known as the attribution problem. If a satellite malfunctions between April 24th and 26th, the statistical likelihood is not insignificant. But what was the precise cause? Was it the stream from the coronal hole, the solar active region, or the elevated electron flux? Or Could a portion of the blame lie with the Earth's passage through the comet's plasma tail? For satellite operators, this distinction is often academic. Their reality is that a failure or emergency safing procedure occurred during a period of intense space weather. In this operational context, the comet is neither credited nor blamed. In public perception, however, the story is often very different. Any satellite anomaly reported during this time could easily be seized upon as proof of the plasma tail's influence, especially among those already inclined to link the comet to the week's events. This is a mirror image of the scientific process. A scientist seeks to isolate a true signal from a noisy background by methodically subtracting all other known influences. The public narrative, by contrast, often does the opposite. It identifies an unusual event and assigns it to the most sensational cause, skipping the crucial work of elimination. The outcome is a self-sustaining cycle of confirmation bias, where every new occurrence seems to validate the narrative, no matter the actual cause. And this points to the most significant risk of the week. It is not the threat of earthquakes triggered by plasma or of widespread satellite failures from a comet's tail. The true danger is far more subtle and human, the pervasive tendency to confuse coincidence with causation. This cognitive shortcut is a powerful force, one that no amount of scientific explanation seems able to completely dismantle. While these invisible dramas play out in interplanetary space, another celestial event is taking center stage. This one, however, is beautifully and easily visible, drawing public attention skyward and, in doing so, adding a final layer of potential confusion to the week's events. The Lyrid meteor shower is reaching its peak. The Lyrids appear each April as our planet travels through the debris left by Comet C 1861 G1 Thatcher. It is essential to note that this is a completely different comet, with no connection to Pan-STARRS. Comet Thatcher itself was last observed in 1861, and its debris trail is well mapped, predictable, and entirely distinct from the other phenomena occurring. Under ideal conditions, the Lyrid shower typically produces about 10 to 20 meteors per hour at its peak, with some years occasionally surprising observers with larger outbursts. The timing of the Lyrid's arrival is almost theatrical. Earth finds itself simultaneously passing through two distinct cometary features: the visible debris trail of one comet and the invisible plasma tail of another. One event produces a spectacular light show for all to see, while the other is entirely imperceptible, requiring sensitive instruments and months of careful analysis to even confirm its presence. One phenomenon illuminates the night sky, while the other might, at best, leave a faint 1 part per million signature in a dataset that only a handful of scientists will ever see. This contrast brings us back to the theme of perception versus reality. The Lyrids will undoubtedly draw widespread attention to comet-related events, but this focus, while genuine, is fundamentally misleading about where the true scientific novelty lies. Inevitably, online discussions about the Lyrid meteor shower will merge with conversations about Pan-STARRS and its plasma tail. This risks conflating visible, harmless meteors with the separate scientific challenge of detecting an invisible plasma tail. The Lyrids are a beautiful spectacle, but their timing makes them a distraction from the subtle, instrument-dependent event that represents the week's most unique scientific opportunity. To complete this crowded celestial calendar, one more astronomical event will feature in lists of converging phenomena this week. On April 24th, the Moon reaches its first quarter phase. The Moon's gravitational pull on our planet is both real and profound. Its most obvious effect is driving the ocean tides, but it also produces, to a much smaller extent, solid Earth tides. These are genuine, subtle deformations in the planet's crust caused by the same gravitational gradient. This raises an intriguing scientific question that researchers continue to explore. Could the changing crustal stress from this tidal loading have any influence on the timing or occurrence of earthquakes? While the literature on space weather's influence on seismicity is often speculative, the statistical analysis connecting tidal forces to earthquakes appears slightly more grounded. In certain fault systems, researchers have noted a faint statistical signal, a weak preference for some earthquakes to occur near the hindi of tidal stress. This raises a natural question about the moon's role in the events of this week. However, it is crucial to understand that a weak statistical preference is vastly different from a conclusion that the moon directly causes earthquakes. Where this effect has been measured, its influence is minuscule when compared to the immense tectonic forces that drive our planet's geology. Furthermore, the first quarter moon phase is not, from a seismological standpoint, a particularly significant alignment. The most extreme tidal forces are exerted during the new and full moons, known as syzygy configurations. This is when the sun and moon align, their gravitational pulls combining to create the strongest tides. In contrast, the first quarter phase is an intermediate configuration called a quadrature, where the sun and moon form a 90-degree angle from our perspective on Earth. During a quadrature, tidal forces are actually approaching their monthly minimum, not their maximum. If one were to build a case for a tidal trigger for seismic events this week, the lunar phase would be one of the weakest pieces of evidence to choose. Its presence in the list of events seems more a matter of calendrical coincidence than one of physical significance. The instinct to include it, to view the lunar phase as another sign of a meaningful convergence, is the very same instinct that can mistake solar wind fluctuations for the signature of a comet. It is the human tendency for pattern recognition outpacing the available evidence, a natural habit that both scientists and informed observers must consciously resist. To see this clearly, let us name all 5 major events unfolding. By placing them on the table together, we can examine them with the seriousness they deserve, avoiding both sensational hype and premature dismissal. The convergence is real, and its rarity is undeniable. First, we have Comet Pan-STARRS, which is making its perihelion passage inside the orbit of Mercury. Earth is positioned in such a way that it is projected to cross the comet's ion tail between April 24th and 26th. A genuinely uncommon orbital arrangement. Second, active region 4420, a sunspot with beta-gamma magnetic complexity, is present on the Earth-facing side of the Sunday. It is producing ongoing flare activity and introducing variability into the interplanetary magnetic field. Third, a high-speed stream from a coronal hole is forecast to reach Earth around April 24th. This is expected to bring solar wind speeds of 600 to 700 kilometers per second and generate geomagnetic activity rated from KP4 to 5. Fourth, an ongoing aftershock sequence continues in the Japan Trench, following the magnitude 7.4 to 7.5 megathrust earthquake that occurred on April 20th. And fifth, the Lyrid meteor shower is reaching its peak as Earth crosses the debris trail of Comet Thatcher, with the first quarter moon illuminating the sky on April 24th. Now, let us consider these 5 events with intellectual honesty. On its own, any one of them could generate a science news headline during a quiet week. In isolation, each is an interesting phenomenon. Seeing them all happen within the same 4-8-hour window feels extraordinary. It feels like it must mean something. The critical question is whether that feeling corresponds to any physical reality. The straightforward answer from the world of physics is no. At least not in the way our intuition suggests. These events are driven by completely independent physical systems. The comet travels along an orbital path determined by its formation billions of years ago and its gravitational history. The sunspot region emerged from magnetic flux on the solar surface, following a cycle of solar activity that has no connection to cometary geometry. The coronal hole stream is a feature of the Sun's rotating magnetic topology, formed long before the comet's alignment became apparent. The Japan Trench earthquake was driven by the subduction of the Pacific Plate, a geological process operating on timescales of tens of millions of years. And the Lyrids follow a celestial calendar determined by Comet Thatcher's entirely separate orbital debris. None of these systems is aware of the others. They do not influence each other in any meaningful physical sense. They are coincident in time, much like a passing car, a soaring bird, and a falling leaf might all cross your field of view in the same moment, not because they are connected, but simply because you happen to be watching. Human pattern recognition, however, perceives something more. It sees these 5 events and instinctively constructs a narrative around their simultaneity, assigning a deeper significance to their convergence. It prompts us to ask, why now? As if now were a special coordinate in the universe's causal fabric, rather than simply the present moment, which will always contain whatever events happen to be active. Every week is now to someone, but most weeks do not feature 5 headline-generating events at once, and so they do not trigger this narrative reflex. The statistical rarity of this specific combination, 5 events of this approximate magnitude occurring in the same 4-8-hour window, has been estimated at around 0.1 to 0.5%. This is certainly rare in the everyday sense of the word. Yet, when viewed across the vast history of the solar system, across the billions of years Earth has orbited the Sun, this specific configuration, or one very much like it, has occurred countless times before. We are not special for experiencing it. We are merely the observers present at this particular instance. This leads to a deeper point, one that connects directly back to the central question of whether Pan-STARRS' tail will be detected. The rarity of the convergence is, in fact, partly responsible for the scientific opportunity it presents. The very fact that a comet is near perihelion, that it has an active ion tail, and that Earth happens to be in the right geometric position to cross its projection, is rare precisely because it requires multiple independent orbital and physical factors to coincide. The rarity is real, but the significance of the convergence as a single unified event is an illusion. What is truly worth holding onto from this moment is the unique observational window it creates. Having multiple unusual conditions active simultaneously means that multiple unusual datasets are being collected. Scientists studying solar interactions, geomagnetic variability, and seismic behavior all have a wealth of interesting data from this period. The interpretation of each piece of that data will proceed independently, using the methods appropriate to each scientific field. The results will eventually be published in separate papers, aimed at distinct scientific communities, each adding a small piece to our collective understanding of the cosmos. While no individual scientific paper will argue that these events were causally connected, their simultaneous occurrence offers something perhaps more valuable: an unusually rich picture of what a particularly active week looks like across multiple physical systems at once. To a scientist, this is what alignment truly means, not a mystical sign, but a powerful and complex data set. This brings us to a crucial concept for understanding this story: a cognitive bias we can call the probability trap. This specific week in April serves as a perfect illustration of this mental pitfall, one with very real implications for how you interpret not just this narrative, but the vast stream of information you will encounter for years to come. The trap works in a predictable way. You witness 5 seemingly rare events, all taking place within the same 4-8-hour window, and you do what any reasonable person would. You try to estimate the odds. You begin by assigning a frequency to each event. For illustrative purposes, let's say each of the 5 events is roughly a once-per-month occurrence, which is broadly consistent with the real-world frequencies. A magnetically complex active region on the Sun facing Earth might happen once or twice a month. A high-speed stream from a coronal hole reaches our planet several times a month, though its presence is not constant. A significant earthquake sequence in a major subduction zone is uncommon, but not truly rare when considering the entire globe. A comet reaching perihelion inside Mercury's orbit, with a tail geometry that crosses Earth's path, is genuinely rare, but one can still estimate a base rate. Finally, a meteor shower peak is a predictable, regular event on the astronomical calendar. Assuming these events are independent, a fact we have already established, as these systems do not interact, the next logical step is to multiply their probabilities together. If we have 5 once-a-month events occurring in the same 4-8-hour window, out of roughly 730 hours in a month, the resulting calculation yields a number that feels extraordinary. You arrive at a figure somewhere in the neighborhood of 1 in 25 million, perhaps even lower depending on your specific assumptions. The exact number is less important than the feeling it creates. It sounds like a figure that simply cannot be a coincidence. It sounds, quite frankly, like it must mean something. But there is a fatal error hidden within this calculation. The mistake is so common, so seductive, and so frequently overlooked that it has its own name in the field of statistics, the look elsewhere effect, also known as the multiple comparisons problem. Once you learn to see this error, you will begin to notice it everywhere. The calculation itself correctly computes the probability of times these specific 5 events times happening together in times this specific window. That part is mathematically sound. The error is its complete failure to account for times you are performing the calculation in the first place. You are calculating the probability of this convergence because you noticed it, because something unusual appeared to be happening, and you wanted to quantify just how unusual it was. That very act of noticing, of selecting this particular window for analysis because it seemed remarkable, introduces a profound bias that inflates the perceived significance by an enormous factor. The question you are really asking is not, what is the probability that this specific combination of events occurs in this specific window? Instead, you are implicitly asking something closer to, given that I am always scanning a continuous timeline of events and will stop to calculate the odds whenever something looks unusual, how often will I find windows that look like this? And the answer to that second, more honest question is regularly. In fact, almost constantly. This is because there are always multiple events occurring simultaneously across the solar system, across Earth's tectonic plates, and across the astronomical calendar. The human brain is extraordinarily, almost embarrassingly, good at finding subsets of these events that can be framed as a meaningful convergence. We are, at our core, pattern recognition machines. In most evolutionary contexts, this was a fantastic survival feature. Spotting the connection between 2 events that were actually related, like the rustling in the grass and an approaching predator, was essential. The cost of a false positive was low, but the cost of missing a real connection was high. Consequently, we evolved to err heavily on the side of finding patterns. A thought experiment can make this problem more concrete. Pick any 4-8-hour window from the past 10 years, completely at random. Now, go back and identify the 5 most unusual space weather, seismic, and astronomical events that happen to overlap with it. You will find something compelling almost every single time. This is because there are always active regions on the sun, always aftershock sequences somewhere on the planet, always meteor showers on the calendar, and always solar wind disturbances of one kind or another. The question is never whether you can find a convergence. The real question is whether the convergence you found means anything beyond the simple fact that you were looking for it. This is not an abstract philosophical exercise. It matters directly for the story we are telling. The same principle that makes 5 events in 48 hours seem impossibly significant is the exact same principle that makes false positives in scientific data appear so compelling. When a scientist sits down with a dataset from April 24th through 26th and begins looking for a comet tail signature, they are subject to this very same cognitive pressure. The brain wants to find the pattern. The brain is good at finding patterns. And if the analyst is not extremely careful, if they do not apply the right methodological safeguards before they even open the data, they will likely find something that looks like a comet signature, whether one is truly there or not. This is not because they are dishonest or incompetent, but because the human visual and analytical system, when left to its own devices, will generate apparent signals out of random noise with remarkable efficiency. This is a fundamental challenge of doing science. This is precisely why the rigorous scientific response to such problems involves steps that can look, from the outside, almost absurdly conservative. Pre-registering a hypothesis, for instance, means writing down exactly what you plan to look for and what will count as a detection times before times you ever open the dataset. This prevents you from unconsciously adjusting your definition of a signal after you have already seen what the data looks like. Another safeguard is applying corrections for multiple comparisons, which means accounting mathematically for the fact that if you test 20 possible hypotheses in one dataset, you should expect roughly one of them to appear statistically significant by chance alone, even if none of them are real. These are not arbitrary hurdles. They are the essential disciplines that separate a true discovery from the echoes of our own expectations. To ensure a finding is real, science employs a kind of immune system, a set of principles designed to protect against human bias. One such principle is blind analysis, where the person running the statistical test has no knowledge of which data points correspond to which events. This prevents any unconscious desire for a particular outcome from influencing the results. Another is the demand for independent replication, which holds that a discovery only gains credibility after an entirely separate team, using different instruments and data, confirms the same phenomenon. These are not mere bureaucratic hurdles or signs of a community that is overly cautious for its own sake. Instead, they represent the hard-won tools of scientific inference. These methods were not gifted to us by evolution. We had to forge them ourselves over centuries of painful experience, learning how easily we can be misled when we mistake compelling noise for a rare, genuine signal in complex datasets, like those from heliophysics. The scientists who will eventually study the spacecraft data from April 24th to 26th will adhere to these exact, rigorous methods. Their process will not involve opening the data, finding something interesting near the predicted time of the crossing, and immediately issuing a press release. Instead, they will establish their detection criteria before they even look at the relevant information. They will define in advance what specific combination of magnetic field signatures, density anomalies, and ion composition changes would count as a confirmed detection, an ambiguous result, or a non-detection. They will also calculate the expected rate of false positives, taking into account all background conditions like coronal hole streams and active region activity. Consistency across multiple spacecraft at different locations will be required. Finally, their work will undergo peer review, where uninvolved scientists will scrutinize every methodological choice, pushing back against any hint of motivated reasoning. This process is slow and unglamorous, yielding results over months or years, not hours or days. This deliberate pace is precisely what the data requires, because the data itself is indifferent to our narratives. It has no awareness that we have a 4-7 hour window and a story that feels like it deserves a dramatic conclusion. The data is simply a collection of numbers, and those numbers will reveal what they will. The only way to understand what they are truly saying, rather than what we wish they would say, is to rigorously apply this scientific immune system and allow it to function. Whether that rigor is rewarded with a genuine detection or simply confirms a null result is a matter left entirely to physics. The outcome does not depend on the convergence of events, how remarkable the timing feels, or how many phenomena cluster together. It depends only on physics. And to speak of that physics, we must turn our attention to where it unfolds. At this very moment, spacecraft are positioned 1.5 million kilometers from Earth, collecting the very data that will one day answer the questions we have been building toward. What these spacecraft are, what they measure, and why their placement is as critical as any other part of this story is where we must go next. Part 17, where the evidence will come from. 1.5 million kilometers from our planet, at a point of perfect gravitational equilibrium, where the Sun's pull and Earth's pull cancel each other out, orbits a small fleet of uncrewed spacecraft. Most people have never heard of them. They produce no spectacular images and never trend on social media. Yet they represent our only real hope of detecting a signal as faint as a comet's ion tail within the roaring, turbulent plasma of the inner solar system. This location is the first Lagrange point, or L1. What is stationed there today is the closest thing humanity has to an early warning system for everything the Sun might send our way. To grasp why L1 is so important, you must visualize the geometry of our solar system. Earth travels through space at approximately 30 kilometers per second, completing its year-long orbit around the Sunday. Meanwhile, the Sun is constantly exhaling a stream of charged particles in all directions, the solar wind, which travels at hundreds of kilometers per second. Consequently, any disturbance heading for Earth, whether it's a coronal hole stream, a coronal mass ejection, a density enhancement, or even the theoretical plasma tail of a comet, must first pass through the L1 point. This occurs roughly 45 to 60 minutes before the disturbance reaches our planet. That brief lead time may not seem like much, but it is enough to trigger alerts, warn satellite operators, help power grid managers prepare, and, for our purposes, record the incoming plasma environment in pristine detail before it becomes entangled with Earth's own magnetosphere. For the question of detecting Comet Pan-STARRS' tail, 3 spacecraft are of particular importance: ACE, D, SCOVA, and Stereo A. Each one contributes a unique capability to the investigation. Together, they form an observational network far more powerful than any single instrument could be on its own. It is a testament to how collaborative science can achieve what individual efforts cannot. Let us begin with ACE, the Advanced Composition Explorer. Having been in operation since 1997, it is a true veteran of the L1 fleet, a silent sentinel that has spent nearly 3 decades monitoring the solar wind from the same gravitational perch. For most routine space weather applications, ACE is respected but not considered glamorous. It measures, it archives, and it has done so with such reliability that its data record has become one of the most valuable continuous datasets in all of heliophysics. Its significance comes not from any single extraordinary measurement, but from the sheer duration of its record, which provides a context that newer instruments simply cannot match. When an unusual signal appears in ACE data, scientists can compare it against 27 years of baseline measurements to determine if the event is genuinely anomalous or just part of the normal range of solar wind variability. That historical context is simply irreplaceable. However, ACE's specific superpower for the Pan-STARRS investigation lies in its ability to analyze ion composition. Its Solar Wind Ion Composition Spectrometer, or SWICS, can measure the charge, state distribution, and elemental abundance of ions in the solar wind with a precision that remains unmatched among the operational instruments at L1. This capability is critical because the most definitive chemical signature of a comet tail crossing is not a change in the magnetic field or a shift in density. Both of those can be caused by ordinary solar wind structures. The most diagnostic signal is a compositional anomaly. Specifically, It is the presence of ions whose charge states are inconsistent with having been formed in the solar corona, pointing instead to a much colder, more exotic origin, exactly the kind of fingerprint a comet would leave behind. The ions that form a comet's tail are born through photoionization, a process where outgassed molecules are transformed at relatively cool temperatures near the nucleus. This origin gives them a distinct charge signature, setting them apart from ions forged in the multi-million-degree furnace of the solar corona. Should Comet Pan-STARRS' tail leave any chemical evidence in the plasma arriving between April 24th and 26th, the ACE spacecraft is our most capable instrument for detecting it. Yet, a significant complication looms. A high-speed stream from a coronal hole is expected to arrive simultaneously, and this solar wind event also alters the ion composition in its own characteristic ways. Fast wind from these holes exhibits a different elemental makeup and ion abundances compared to slow wind. While these solar effects are well documented and could theoretically be modeled and removed, the challenge is subtracting a massive, understood signal to reveal a tiny, uncertain one, hidden beneath an analytical task, demanding months of meticulous work. No one will glance at ACE data on April 26th and declare a comet detection. The composition analysis alone will require weeks at minimum. A different instrument with an entirely different mission is DSCOVR, the Deep Space Climate Observatory. Whereas ACE is a research platform for detailed composition analysis, DSCOVR is an operational monitoring system. It is the principal real-time data source for NOAA's Space Weather Prediction Center, with sensors continuously measuring the solar wind's speed, density, temperature, and magnetic field. This information is transmitted to Earth and made public with a delay of only minutes. If you have viewed real-time solar wind conditions online, you were almost certainly observing DSCOVR data. It acts as the vital heartbeat monitor for the L1 spacecraft fleet, not the most scientifically advanced, but the most crucial for operations and the most accessible for detecting pan-stars. For this event, DSCOVR's magnetic field data is especially relevant. A comet tail crossing should cause a specific rotation in the interplanetary magnetic field. This signature, shaped like a hairpin, results from the solar magnetic field draping around the cometary obstacle. Such a feature would appear in DSCOVR's magnetometer if it is strong enough, but therein lies the great uncertainty. Will the signature be prominent enough at Earth's distance from the comet? And can it be differentiated from the magnetic disturbances the coronal stream will generate? This is the central puzzle. DSCOVR will clearly detect the coronal stream. Whether it can also perceive the faint whisper of the comet beneath that roar is a question no one can answer in advance. The story then expands into 3 dimensions with Stereo A, whose contribution is perhaps the most underappreciated. The Stereo mission, or Solar Terrestrial Relations Observatory, began with a pair of spacecraft intended to capture the first stereoscopic images of the Sun and its solar wind. The concept was simple. One spacecraft would orbit ahead of Earth, the other behind. Their combined perspectives would build 3D models of solar wind structures, much like our eyes create depth perception. While Stereo B was lost to a communications failure in 2014, Stereo A continues its mission. It is currently positioned tens of degrees ahead of Earth in heliocentric longitude, offering a crucial, laterally displaced view of the same interplanetary space. This unique lateral displacement is what makes Stereo A so valuable. A comet's ion tail is not a simple sheet. It is a complex 3-dimensional structure with varying width, depth, and density. As Earth travels its orbit, it will slice through one specific cross-section of this tail. Meanwhile, Stereo A, approaching from a different angle and at a different moment, will pass through another. If both spacecraft register anomalies that align with the tail's predicted 3D geometry for their locations, the resulting multi-point correlation is far more compelling than any single detection could be. This powerful technique, the decorrelation test, is one of our best tools for distinguishing a real signal from random noise. The logic behind this test is a study in contrasts. Solar wind fluctuations, whether from coronal hole streams or general turbulence, do not remain perfectly correlated between two spacecraft separated by tens of millions of kilometers. Any correlation diminishes with distance and time. A vast coherent structure like a comet's tail, however, should generate predictable anomalies at both spacecraft, determined by its geometry, using orbital mechanics. Scientists can calculate when each spacecraft should encounter the tail and what the signal should look like. If the data from both observatories matches these predictions, the case for a detection grows immensely stronger. Conversely, if only one spacecraft sees an anomaly, or if the signals do not conform to the model, the case dissolves. Right now, data from all three spacecraft is streaming to Earth. Some is publicly available on space weather portals within minutes. The instruments are working, the window is open, and the celestial geometry is aligned. The primary obstacle has never been acquiring the data. The true challenge is interpretation, knowing what to look for, and possessing a model sophisticated enough to understand what is seen. This is made profoundly harder by the coronal hole stream, which generates signals orders of magnitude stronger than any trace the comet might leave. The answers are there, embedded within the data, but finding them will be a monumental effort. For the next few months, researchers will be carefully sifting through a torrent of solar data, hoping to determine if any answers can be heard above the sun's constant noise. But what, precisely, are they searching for within that information? The mission is to find the exact signatures in the correct sequence that would form the basis of a credible detection. This is the journey we must now undertake. Part 18. What scientists are truly seeking. Imagine a heliophysicist seated before a terminal on April 24th, their screen alive with multiple, simultaneous data streams. Solar wind speed, the direction of the magnetic field, proton density, and the ratios of ion composition are all updating in near real time, sometimes every few seconds. Somewhere within this cascading river of numbers, a faint signal might exist, a message from a comet that has not graced the inner solar system for thousands of years. Of course, it is just as possible that no such signal is present. To find out, one must know not only what to look for, but also what to disregard. During this crucial week, the data will be filled with phenomena that mimic a true detection, but are, in fact, something else entirely. So, let us explore the anatomy of a genuine discovery. What does a comet tail crossing actually register as in spacecraft data? What are the specific markers, and in what order must they appear to constitute a believable event? And why is each individual marker insufficient on its own, requiring the presence of all of them before any scientist can responsibly announce a finding? The first and most prominent indicator is a rotation in the interplanetary magnetic field, IMF, that follows a very particular profile. This is not just any random fluctuation. The IMF is in a constant state of change as various solar wind structures pass by the L1 monitoring spacecraft. What distinguishes a cometary tail rotation is its unique shape and the geometry of its formation. To grasp this, one must first understand the process of magnetic draping. As Comet Pan-STARRS makes its fiery journey through perihelion, well inside Mercury's orbit, it is actively outgassing immense clouds of neutral molecules into space. Solar radiation almost instantly ionizes these molecules, transforming them into charged particles that can interact with the solar wind and its embedded magnetic field. The solar wind cannot simply pass through this newly formed plasma as it does through empty space. Instead, it must flow around this obstacle, much like a river diverting around a large boulder. As the solar wind flows around the comet's ionosphere, it drags the magnetic field lines along with it. These lines are stretched, bent, and wrapped around the cometary obstruction, pulled far out behind the nucleus to form the tail. If one could view this structure in cross-section, it would resemble a folded hairpin. This configuration consists of two lobes of magnetic field draped around the nucleus and extending backward, with the field in one lobe pointing generally toward the Sun, and the field in the other pointing away from it. Separating these two lobes is a thin current sheet running down the tail's center. When a spacecraft traverses this structure from one side to the other, its instruments record a highly specific sequence. The magnetic field vector doesn't just flip erratically, it rotates in a predictable pattern. The field's magnitude gradually increases as the spacecraft nears the tail's boundary. Then, as it crosses the central current sheet, it makes a sharp change in direction. Finally, the sequence reverses symmetrically as the spacecraft emerges from the other side. This distinct shape, the gradual approach, the sharp central turn, and the symmetric exit serves as the magnetic fingerprint of a tail crossing. This is precisely the signature that the Ulysses spacecraft recorded when it passed through Comet Hayakutake's tail in 1996, a discovery buried in the data and not recognized until the year 2000. It is this same theoretical target that the D-SCOVA magnetometer and the ACE magnetic field instrument will be scanning for during the April 24th to 26th window. The primary difficulty is that this signature, while clear in a clean dataset, can be partially imitated by other solar wind phenomena. Sector boundary crossings, CIR boundaries, and various magnetic discontinuities are all generated by the Sun itself. A coronal hole stream, expected to arrive during the observation window, will produce its own magnetic rotations and sharp directional changes, making the task of differentiation incredibly complex. This is why context, density, composition, and geometry is critical, and why no single indicator can stand alone. The second key indicator is a decrease in proton density within the tail. The physics behind this is quite intuitive. The plasma streaming from the comet's nucleus is not dense enough on its own to significantly increase the total particle count at Earth's distance. Instead, its primary effect is to partially displace the ambient solar wind. Consequently, the region inside the tail contains a mixture of cometary material and a reduced amount of solar wind material compared to the surrounding space. The result is a measurable dip in proton density as a spacecraft enters the tail, creating a valley in the data rather than a sharp cliff. This is characterized by a gradual decrease toward the tail's center, a minimum at or near the middle, and a recovery on the far side. The magnitude of this density drop is one of the great unknowns, depending on the tail's cross-sectional density profile at Earth's distance, a value that models can only estimate with a large margin of error. The most optimistic scenarios predict a density decrease of 10 to 30% relative to the surrounding solar wind. For comparison, the Ulysses crossing at Hayakutake showed a decrease by a factor of 2, which is on the high end of what current models suggest for Pan-STARRS. A 10% drop is, in principle, detectable. However, it demands a stable, well-understood baseline for measurement. This brings us to the core of the analytical challenge. During the passage of a high-speed stream from a coronal hole, the background proton density is already fluctuating by 20 to 40% over mere hours, simply due to the stream's natural structure. Attempting to isolate a subtle 10% dip from the comet against this turbulent backdrop is precisely the kind of problem that cannot be solved with a quick glance at a real-time plot. It requires months of meticulous, patient analysis. The third indicator, and the one that generates the most excitement among scientists, is an anomaly in the heavy ion composition. This is because it provides a chemical fingerprint that is exceptionally difficult for the solar wind to replicate on its own, making it perhaps the most definitive piece of evidence. The key to this signature lies in the unique chemistry of the comet itself. The The solar wind is a stream of particles carrying heavy ions like oxygen, carbon, silicon, and iron. These ions, however, are born in the extreme environment of the solar corona, a plasma simmering at temperatures between 1 and 3 million degrees. In such intense heat, atoms are stripped of their electrons with incredible efficiency, creating ions with high charge states. For instance, oxygen in the solar wind is typically found as O6+ and O7+, while carbon appears as C5+ and C6+. These highly charged states are a distinct signature, a clear fingerprint of their coronal origin. In stark contrast, cometary ions are formed in a completely different, much colder setting. As a comet approaches the Sun, its nucleus outgasses molecules like water, carbon monoxide, and carbon dioxide. Solar radiation then ionizes these molecules at relatively low temperatures, far from any million-degree plasma. This gentle process results in ions with low charge states, such as O+ or O2+ for oxygen. Cometary carbon is often found in molecules like CO+, which is simply carbon monoxide that has lost a single electron. This fundamental difference in charge state is precisely what the solar wind ion composition spectrometer on the ACE spacecraft was designed to find, not just more oxygen, but oxygen and carbon with the wrong charge, a sign they could only have come from a cold, cometary surface and not the Sun's fiery corona. Among these potential indicators, one molecule stands out as a nearly definitive piece of evidence: ionized carbon monoxide, or CO+. This particular molecular ion is not produced in any meaningful quantity by the Sun itself. The corona simply does not outgas carbon monoxide. Its presence, therefore, points almost exclusively to a cometary source. If the ACE spacecraft were to register a spike in CO+ above its normal background noise during the crossing window of April 24th through 26th, that detection would serve as a chemical smoking gun. It would be close to undeniable proof of an encounter with cometary material. The crucial question, however, remains one of sensitivity. Is the concentration of CO+ within the diffuse tail of Pan-STARRS at Earth's vast distance from the comet substantial enough to rise above the instrument's detection threshold amidst the noisy environment of space? But what if no single, clear signal emerges? In cases where a smoking gun is absent, scientists can turn to a broader analytical method known as statistical stacking. This approach becomes vital when no individual measurement is compelling on its own. Instead of relying on one perfect textbook signal from a single instrument, statistical stacking searches for consistent, subtle patterns across multiple instruments and over extended periods. It considers the full three-dimensional geometry of the predicted crossing. If the orbital models pinpoint the center of the crossing at a specific time, and that exact moment corresponds with even marginal anomalies in the magnetic data, the density data, and the composition data simultaneously, the combined statistical weight of these faint signals can become significant. It is a form of scientific triangulation. While no single line of evidence points definitively to the answer, multiple lines, all converging on the same location in time and space, are far more difficult to dismiss. Ultimately, no amount of analysis can predict whether the data will cooperate. We cannot know in advance if a detectable signal was left behind, or if it will be distinguishable from all the other activity occurring in the same window of time. The laws of physics either imprinted a mark on the solar wind, or they did not. Therefore, the most probable outcome of the coming months of work is not a simple yes or no. It is far more likely to be something more honest, more uncertain, and, in its own way, more interesting than either of those binary answers. It is important to be honest about probability, setting aside the sensational numbers that make for dramatic headlines. We must instead make a straightforward, unsentimental assessment of what is most likely to happen as scientists analyze the dataset from April 24th to 26th. They are searching for the ghost of a comet that may or may not have left a trace. We must consider all the challenges. The expected diffuseness of the tail so far from the nucleus, the already elevated solar wind background, the ill-timed arrival of a high-speed stream from a coronal hole, and the additional magnetic complexity introduced by active region AR 4420 on the Sun. Given these immense hurdles, what does the landscape of realistic outcomes actually look like when ranked honestly by likelihood? The most likely outcome is this. Earth does, in fact, cross through a region of space geometrically associated with the ion tail of Pan-STARRS. The crossing is physically real. Our planet moves through a volume that contains, or recently contained, material from the comet's nucleus. However, the spacecraft data from that window yields no clearly identifiable signal. This is not because nothing happened, or because the tail was absent. It is because the signal-to-noise ratio, under the actual conditions that prevailed, was simply too low for a confident identification. The event occurs, and the instruments record it faithfully, just as they record everything, without knowing what they are supposed to see. And the cometary signature, if it is present in the data at all, remains buried below the threshold where it can be confidently separated from everything else happening at the same time. This outcome, it must be said, is not a failure. It can be easy to interpret the language of detection and non-detection as a story of success or error, but here, nothing went wrong. The geometry was correct, the instruments were functioning perfectly, and the scientists were watching diligently. But nature does not owe us a clean signal, and the conditions during this event were genuinely unfavorable for extracting a subtle one. The resulting ambiguity is itself informative. It tells us something about the density of Pan-STARRS' tail at Earth's distance, and about the coherence of its structure across nearly half an astronomical unit. A non-detection under known noise conditions is a constraint. It is data. It is not an empty result, but a quiet piece of the cosmic puzzle. A second, more probable outcome is what scientists refer to as a null result. It is crucial to understand that this is fundamentally different from the ambiguous scenario previously discussed. In an ambiguous case, the data presents intriguing signals that cannot be conclusively linked to the comet, but also cannot be dismissed. A true null result, however, is far more definitive in its silence. Here, the signatures from the coronal hole stream and the active region would be so powerful that they completely dominate the data. Any subsequent analysis would reveal nothing above the background noise that could be credibly connected to cometary material. Even if the geometry of the tail crossing was perfect, the data itself would offer no positive confirmation. The comet would have, in essence, passed through our instruments like a ghost, leaving no discernible trace in any dataset. From a human standpoint, this is perhaps the most disheartening possibility, as it eliminates the chance of a future breakthrough. With ambiguous data, there is always hope that new models or more advanced analytical tools might one day unlock a hidden discovery. But with a genuine null result, there is simply nothing left to find. The signal was either too faint to be detected at this distance, or it was so thoroughly drowned out by solar noise that it is lost forever. The chapter would simply close, unresolved. A third possibility, less likely than the first two but still plausible, is that one or more of our spacecraft might register what could be called a tentative anomaly. This would be a signal that, upon close inspection, shares some expected characteristics of a tail crossing, but isn't a perfect match. For instance, the magnetic field might show a rotation that has the right general shape, but lacks textbook clarity. The data could reveal a slight dip in density around the predicted time, falling just within the model's margin of error. Perhaps the composition data from the ACE spacecraft would show a subtle, unusual shift in the charge state of heavy ions, not clearly anomalous, but noteworthy enough to be flagged. Individually, none of these signals would be compelling enough to stand as a standalone claim of detection. Yet, the fact that several small indicators all point in the same direction, all occurring around the predicted time, makes this the most scientifically interesting short-term outcome. It may not be the most satisfying, but it is the one that ignites a new line of research. It presents a puzzle that demands to be solved. A team of scientists, noticing this faint cluster of marginal signals, might decide it warrants a deeper investigation. They would pull the complete composition dataset from ACE, dedicating weeks to a meticulous charge state analysis. They would then compare the data from stereo A against the data from L1, searching for a sequence of anomalies that aligns with the geometric predictions of a tail crossing. Slowly, methodically, they would construct a case, ensuring that every step is accompanied by explicit uncertainties. Eventually, this work might culminate in a scientific paper that frames the event as A times possible times detection of Pan-STARRS' ion tail. The authors would heavily stress the word possible, carefully quantifying the uncertainties and detailing all the alternative explanations they considered. That paper, if it is ever written, will take a great deal of time. The peer review process in heliophysics is not known for its speed, and a detection claim of this nature, rare, contested, and reliant on subtle correlations across multiple instruments, would face immense scrutiny. Reviewers would challenge the methodology, demanding additional corrections, new comparisons, and more rigorous tests of alternative theories. The authors would revise their work, and the debate would begin. It's even possible that a different group of scientists could publish a second paper with a conflicting conclusion, or at least a more conservative interpretation of the same evidence. This back and forth is the heartbeat of scientific progress, a slow, sometimes frustrating process that rarely yields a clean, definitive answer on the first attempt. This reality is important to grasp. Anyone hoping for a press release on April 26th confirming that Earth crossed the comet's tail will almost certainly be disappointed. That is simply not how this kind of science operates. The drama of the 4-7-hour window can inflate expectations, but it's vital to state plainly that this window is for data collection, not immediate discovery. Once the window closes, the data is archived, and the scientists return to their other projects. The truly interesting analysis then begins quietly, on a timeline completely detached from the news cycle. Then, of course, there is the genuinely thrilling possibility, the one that would be unambiguous and would not require months of painstaking argument. This is the scenario where the signal appears so clearly in the data that multiple instrument teams independently notice something extraordinary within the same time frame. It would look like a clean, interplanetary magnetic field rotation with the classic hairpin profile of magnetic draping. It would involve a proton density decrease of 20% or more, lasting for several hours and centered symmetrically around a minimum point. Simultaneously, the ACE spacecraft would detect an anomaly in its composition data. Low charge state heavy ions that are inconsistent with any known solar wind source. To cap it all, stereo A would observe a consistent signal at precisely the geometrically predicted time. With all four indicators present across multiple spacecraft, the evidence would be so clear that scientists monitoring the data in real time might actually say to one another, that might be it. This outcome, however, is the rarest of all realistic scenarios. It is not impossible. The physics allows for it, and the geometry is favorable. If the comet's tail happens to be denser and more coherent than conservative models predict, it could indeed happen. But the solar weather conditions make it the least likely of the near-term outcomes. The coronal hole stream is simply too loud, and the active region is too turbulent. The background noise is so high that the comet's signal would need to be significantly stronger than currently expected to stand out clearly from everything else arriving at the same time. So, what does the scientific community's actual working posture look like? Based on informal discussions and the thinking that surrounds such events, it is a stance of patient vigilance. The plan is to watch the data carefully, flag anything that appears interesting, and preserve everything meticulously. There is no expectation of resolution on a 4-8-hour timescale. If a conclusion is to be reached, it is expected to happen on a scale of 6 to 12 months, and perhaps even longer. We need only look to the past for context. The confirmation of the Hayakutake tail crossing took 4 years to emerge from archived data. This event might take 2 years, or 5, or it might never emerge at all. This is what science truly looks like from the inside. A slow, deliberate, and often uncertain search for understanding. This is not a story that unfolds with the immediate drama of a countdown clock, where an answer is guaranteed at 0. Instead, it is a slow, methodical, and at times frustrating excavation. A search for a faint whisper buried within an extremely noisy set of data. It is a journey undertaken by people who are comfortable with uncertainty, a quality often absent in science communication that seeks a simple conclusion. This story, however, may not have a clear ending for a very long time. And it is precisely this ambiguity that makes the pursuit so compelling. The window for direct observation closes on April 26th, but the real story only begins the morning after. This is part 20, the delayed discovery, the true ending. Here is the most probable timeline for how this scientific chapter will conclude. In the days immediately following April 26th, it is unlikely that anything obvious will be reported. The corrotating high-speed stream will have swept past our planet, leaving behind its usual fading geomagnetic effects as space weather conditions gradually return to their baseline. The precious data collected by the ACE, DES, COVR, and Stereo A spacecraft will be securely archived, ready for download. The perihelion passage of Pan-STARRS will become a receding memory as the comet starts its long, slow journey back toward the frigid outer solar system, not to grace our skies again for centuries, perhaps even millennia. The observational window will have definitively closed. In the weeks that follow, a small number of researchers who were specifically looking for a cometary tail signature will begin their meticulous work. They will pore over the archived information, and in all likelihood, they will find a dataset overwhelmingly dominated by the coronal stream and its associated geomagnetic activity. Within this noise, they might flag 1 or 2 brief periods where the data exhibits characteristics that could be consistent with a tail crossing. They will carefully document the immense uncertainties and then start the painstaking process of trying to define these anomalies with greater rigor. It is a search for a single, meaningful note in a symphony of cosmic static. Months later, the analysis will enter a deeper phase. The composition data from the ACE satellite will undergo careful correction. Scientists will subtract the solar wind background, using complex models of what the elemental fractionation pattern from the high-speed stream should look like based on its source. Once that background is removed, a residual signal might emerge, a subtle excess of certain ion types that does not neatly fit the solar wind model. Or, just as possibly, nothing will emerge. The models may describe the data perfectly, leaving no leftover signal to be attributed to an external source. If a residual does appear, the data from Stereo A will be consulted. Does the same anomaly show up there, at the exact time predicted by the orbital geometry? Does it possess the right characteristics? Does the magnetic data offer any hint of a rotation consistent with field lines draping around an obstacle? This critical step of correlating multiple datasets is the key to the entire analysis, and it is the step that will take the most time, requiring careful collaboration between different instrument teams, each with their own calibration standards and methodologies. From this process, a scientific paper begins to take shape. It will be cautious in its assertions and meticulous in quantifying its uncertainties. It will be framed explicitly as an attempt at detection rather than a confirmed discovery, unless the evidence is truly overwhelming. The paper will then enter the crucible of peer review, where other experts will challenge the interpretation and push back on the analysis. The authors will revise their work. In the meantime, another paper from a different research group might arrive at a conflicting conclusion. A quiet, specialized scientific discussion will slowly unfold within the pages of academic journals that most people will never read. At some point, perhaps a year from now, or maybe even 3, the scientific community will arrive at a working consensus. One of 2 conclusions will be reached. Either Pan-STARRS' tail was indeed detected a modest, uncertain, but probable finding, archived as a companion case to the historic encounter with Comet Hayakutake, or it was not. In the second case, the conditions were simply too noisy, and the event would join a much longer list of predicted tail crossings that yielded no confirmed signal. Both of these outcomes are incredibly useful to science. A confirmed detection would add a second data point to a set that currently contains only 1, and for building any physical model, 2 data points are immeasurably more valuable than 1. A non-detection, a null result, is also informative, as it establishes a firm constraint on the density and coherence of comet tails at these vast distances. Science advances just as readily on null results as it does on positive ones, even if they attract far fewer headlines. This is the quiet reality of the scientific process. It does not happen with a flash of revelation on April 26th. There will be no press release confirming that Earth passed through a comet's tail with a neat summary of what happened. The truth is found through a slow, grinding, multi-year process of data collection, analysis, uncertainty, quantification, peer disagreement, revision, and eventual provisional consensus. The most dramatic moment was entirely invisible. The real drama of discovery is purely intellectual, playing out in scientific papers, conference presentations, and quiet arguments over methodology. Consider the precedent. The story of the Ulysses spacecraft and Comet Hayakutake took 4 years to emerge from the data, from a crossing in 1996 to a paper published in 2000. And when that discovery finally did emerge, it was extraordinary. Its significance was not just what it told us about that one specific event, interesting as that was. Its true power was in what it revealed about the possible, about how far a comet's influence can truly extend. It gave us a glimpse of the vast, invisible structures that exist in interplanetary space, things we cannot see but can measure. It showed us how the solar system is woven together by invisible threads of magnetic force and ionized gas that stretch across hundreds of millions of kilometers. Pan-STARRS may or may not add its own chapter to that story. All the ingredients were in place, the geometry was right, the comet was active, and the instruments were watching. Whether the noise of the universe chose to cooperate is another matter entirely. As a rule, the universe does not consult our preferences regarding signal-to-noise ratios. But this is what stays with you, or at least what stays with me, when you contemplate what this event truly represents. Somewhere in the data being collected right now, in the silent streams of numbers flowing from ACE, DSCOVR, and Stereo A, recorded onto drives that will sit in archives for years, there may be the faintest trace of a comet. A comet that formed in the cold outer solar system billions of years ago, swung into the inner solar system for the first time in recorded human history, passed inside Mercury's orbit for a brief, fiery moment, and left behind a ghost of ionized molecules that drifted outward on the solar wind. A ghost that, for 48 hours in late April of 2026, swept over a small blue planet that happened to have instruments sensitive enough just barely to notice. Maybe. Or maybe not. In the end, the data will decide, not the alignment of celestial bodies, not the narrative we wish to construct, not the striking convergence of 5 events in 1 week that our pattern-seeking brains so desperately want to make meaningful. Only the data. And perhaps the most profound truth of all is this: the data does not care about the story. Ultimately, the signal either existed or it did not. The true work of science often happens in the quiet space between an event and its discovery, hidden within archives and obscured by noise. This is rarely a glamorous pursuit, lacking the immediate spectacle of a fireball lighting up the night. Yet, it is from this patient sifting of information that genuine understanding emerges. It raises the question, could this story unfold like that of Hayakutake? In that case, years from now, an analyst might revisit the datasets from April 24th through the 26th, uncovering a detail in the figures that everyone else had overlooked. The drama would have been present from the beginning, simply waiting for our ability to decipher it. If a signal is there, it will not be found by looking up at the sky, but revealed in the very data we almost set aside.